Welcome to OpenBSD and OpenBGPD as a control plane for your ISP. This is a talk for ISPs and for computer network engineers in general and programmers who have an interest in networking. My name is TomSmyth and I'm the Chief Technical Officer of Wireless Connect. We're an ISP in Ireland, and I feel very privileged to be here. I'd like to just thank Dan Langell and all the volunteers of the BsdCAN who've made it happen despite all the odds this year and made it an online course. I also just want to say I'm a net admin, not a dev, and so I haven't written any of the code that I actually use, and I don't speak for the OpenBSD project or any of the BSD projects for that matter. And I'm very appreciative to the BsdCAN team for allowing me to speak here. By using this software and by building my networks, I'm trampling all over the shoulders of giants like Henning Brauer, Peter Hessler, Claudia Ecker, Job Schneiders. There's so many people in the Sebastian, and there's so many people in the OpenBSD project and BSD projects in general that have made my life easier. So all your time and effort has made my working life easier, and it allows us to bring high quality networks to rural Ireland and to businesses all over Ireland. So I'm really appreciative of BSD and what it's done for me in my professional career and what it's done for my company. I'm an engineer and a business owner. I like the road less travelled, and I suppose I love the path to understanding and solving problems. If you can understand a problem, you can solve it. That's my my approach to life. I've been working in IT since 2000, so 20 years, and I started consulting in 2005 and I set up an ISP with my best friends from college, and I haven't looked back since. So when I started with Unix. I suppose it would be back in 1998. I suppose I got a taste of it with Linux, thanks to Dr. Barry McMullen. Tom and BSD, I use FreeBSD actually as an admin or as a user with VPS hosting for customers that we had around 2003-2005. I enjoyed it. I liked the OS. I used OpenBSD then, started using OpenBSD as an SSL terminator because of hostedD and relayed's naming convention. I didn't realize they had one in base, and I actually ended up using Stunnel in front of my reverse proxies in front of my sites. And I gradually increased usage across my ISP. In terms of pretty much now we're running DNS recursive resolvers and authoritative resolvers using the NSD and Unbound, which is in OpenBSD base, which is great. OpenNTPD for maintaining time, which is critical for any timer-based protocols for routing, such as OSPF, and also for keeping obviously logs consistent. We use OpenSMTPD for SMTP relaying for our clients and our customers for alerting for outages and stuff like that, and alerting for alert conditions on our routers. I have to say it's a phenomenal simple program, and the syntax is lovely. And comparing it to the likes of SendMail, I just found it a lot nicer to use. And thanks to Shields and all the lads, all the people who work and contribute to that. I also use OpenBGPD for this talk as a control plane for our ISP, and also as a looking glass. We use that for our support staff as well, so that they can query the routers really easily without having to log in and stuff like that, and they can check to see if everything's okay and do some rudimentary diagnostics, obviously for our customers as well. We use OSPFD and OSPF60, and we also use OpenBSD as NTUs, so network termination units for client premise equipment, so that we can validate the uptime for business customers and provide some filtering services for the business customers. So why do we use OpenBSD or OpenBGPD? Well, you can't fly like an eagle or soar like an eagle if you're flying with turkeys. So I liked the attention to detail I like in terms of the design, the documentation, and the implementation. And thank you, Ingo, and all the people who focus so strongly on quality documentation. And Ingo's had some very interesting talks at BsdCAN and EuroBSDCAN, talking about how, if you actually document something properly, you can identify errors in logic in the programmer's understanding of the problem. I find that the syntax is very brief yet profound, and I can even see that, we often witness that on the tech mailing list where people are discussing the naming of functions, like, is it communicating the proper meaning for a user? And I think that's it's just amazing. And I love it. In terms of stability, security, obviously, these are all names that are synonymous, or descriptions that are synonymous with OpenBSD. For me, it was also confidence in knowing that if something goes wrong, chances are it's something I have done, or maybe there's an external condition such as connectivity problem, backhaul attenuation if someone digs up a fiber cable, and connectivity to third parties. If there's a third party connectivity, is there something there? Having that confidence that your equipment is doing what it says it's doing and doing what you're asking it to do. If you're asking it to do the wrong thing, you can fix that. Your team can fix that. Your team can work together with it. If your system is being honest with you, is it actually telling you what it's doing, or is there a distance between what it's saying and what it's doing? And that for me, you get tired of that. It gets pretty old very quick when you're using other systems that mightn't necessarily have that same alignment of configuration versus what the equipment is actually doing for you. And what I'll be discussing today, I'll be discussing a high-level overview of our network, a routing fundamental crash course, BGP in about 60 seconds, and recursive routes in about 2 minutes. And we'll then go through the whole control plane and data plane, what I mean by that. I'll talk about OpenBGPD and how we used it. So the challenge was to manage, what we wanted to do is manage our network routing with OpenBSD and OpenBGPD. Goes without saying, the syntax, the simplicity, security. I wanted to kind of stop worrying about the network. I wanted to make that business as usual changes didn't actually cause an issue for other clients as you were onboarding a new client. And I was kind of getting tired of closed source products and software quality issues with the same. And I also wanted to achieve multiple line rate speeds with scale. So, when you're using software routers, you have a limited number of network interfaces, and as you try and add further interfaces for other customers, your load is going to increase. And so we kept running into bottlenecks with our software routers. So that was partially the reason why we wanted to change. So the solution we arrived at was OpenBGPD plus Arista hardware switches. So the Aristas on the picture there that you see are Arista 7050 QX32s. So like in terms of the flexibility of OpenBSD, it was like that we had, like, now we can get RPKI route validation. We can also get deny advertisements by default with RFC 8212. And we can the max prefix out limit feature, which Claudio implemented just in 6.6 current and 6.7 release, is just brilliant, and thank you, Claudio, for doing that. I should have tested that more for you, but sorry, my bad. But the max prefix limit out just it saves you. It's your last line of defense if, for instance, you make a mistake in your routing filters. We've all done it at one stage or another, so I would like to minimize the impact of it. So it just limits the impact of those fat finger F-ups. So in terms of, so then we also coupled that with the Arista 7050QX. So no software router is going to compete with, let's say, hardware switches or in terms of forwarding performance. So what we wanted was a bit of flexibility on how we manage the network and a bit more control, but we also wanted to have high speed and more scale. So like with an Arista 750, for example, in our configuration, we get 96 10 gig ports in one U. It's pretty savage, like, you know. And that makes a massive difference. So, you know, you're talking about 2.5 terabits per second and 1.4 billion packets per second. So it's pretty nice, and the latency is, you know, half a microsecond, which is pretty nice as well, you know. So in terms of the VM specs, like, it was, you know, we started using it at OpenBSD 6.3 in terms of when we started trying to control our network more and more with OpenBSD and OpenBGPD. So we installed OpenBSD in a KVM. You know, we were talking about 2 cores, so very modest config. 2 VirtIO NICs for redundancy, for connecting to 2 different layer 2 and layer 3 networks effectively, and then just 1 management NIC for. We used 6 gigs of RAM initially, but we started to kind of, you know, we were approaching memory limits, so we decided to just bump it to 8 gig. So we've actually, you know, put it to 8 gig at present. That's what we're running on our BGP route reflectors. In terms of KVM optimizations, just if you're ever doing it, we increased the tap queue size to 8,000. So the default one is 1,000. So that's the tap. That's the interface that links the virtual NIC of the computer to the underlying hypervisor forwarding plane. So instead of having it at 1,000 bytes, which would be the default, we used 8,000 bytes, and that's particularly useful if the router is busy, or if your VM is busy and is not able to process the package when the hypervisor sends it to it. You'll find out if you need that is if you look at the TX drops on your interfaces on your hypervisor. If you're seeing TX drops on your tap, then that queue will help you just smooth out those microbursts. And it'll just help you a little bit. We turned off kernel same page merging because it's pretty much useless on OpenBSD for OpenBSD guest because of the kernel address-based layout randomization, Carl, and also the ASLR and all that type of cool security mitigations that OpenBSD have implemented. The high-level design, what we ended up with was 2 route reflectors, 2 OpenBSD BGPD routers running in KVM VMs, and then we had 2 Arista switches with a multi-chassis lag between them, and then we had 2 other Aristas which were set up to be our routers. So the reason why we did that, as in used 4 Aristas instead of 2, is that you can optimize the Trident chipsets in it, the Trident 2s, to basically be either optimized for layer 2 operations, like, you know, tunnels and all that type of stuff, or layer 3s, 3 setups where you're actually using them for routers. So what we wanted was an extensive layer 2 setup within our data center, but we also wanted to have the routing capability. So we just said we'd use the 2. I have to say they're pretty impressive with what they have. In terms of IP routing, so now what we've kind of just said, I've kind of painted a picture of what we do, but now I kind of want to talk about the logic behind the design and why we do it that way. So if we look at IP routing, it's basically for a packet that you're sending to a given destination. So a packet comes into your router or is originating from your computer. It has a destination IP. You will forward the packet to another device so that it will hopefully reach the end destination. And so you're routing a packet based on its destination. You don't look at the source, you don't do any of that. And one of the concepts that are really important is longest prefix match. So if you have a more specific route, so a smaller network, and the packet that's destined for a device inside those networks that are referenced in your routes, then you will forward it to whatever the one that is the most specific. And the simplest way of even talking about it is longest prefix match. So the bigger the number in the CIDR notification, that's the slash, the number after the slash in your routes, as we often talk about as network engineers, the more likely that route will actually be picked, or that route will be picked. So if we have an example where we have a routing table with 0.0.0/0, the default route, pointing at 10.1.2.3, and we have 8.8.8.0/24, a common network that most people would know who runs that, and that's going to 10.1.2.4. We can, if we want to then send a packet to 8.8.8.8, so Google's DNS, our device will use which next hop would it use? Well, it would use the 10.1.2.4 route. Why? Because it's more specific. It's a longer prefix match. So it just so if we talk about direct routes and direction of traffic flow. So one route on its own is a unidirect. It'll allow you to forward traffic unidirectional. So unidirectionally. So what do I mean by that is that routes, it'll route based on the destination, and routes learned by you. So if you have a route in your laptop or router, it will forward traffic out. It'll upload. So that would be like your upload on your computer. Routes learned by everyone else about you, that's your download traffic. And that's it's an important point, and it's one that is a fundamental principle behind how this architecture worked well for us in our network. If you're talking about internet conversations, it's something that maybe a lot of non-network engineers kind of take for granted. In order for an internet conversation to happen, like bidirectional communication, hopefully, not like monologues that people will probably complain about Tom when he's talking to them. Sorry about that, guys, everyone. So one of the things you'd be looking at is, so how do you need to route correctly to the other party. The other party needs to route correctly to you. And then all the routers in between you and the other party need to route the packets correctly in both directions. And those paths to and from the other party can be different, and invariably are different on the internet. So if we're talking about Border Gateway Protocol, it allows different organizations. So now we've kind of dealt with the routing setup. Now let's talk about Border Gateway Protocol and what it is. So it's people describe it as the glue that links the internet together or makes the internet happen. What I like to think of it is that it allows organizations who run networks, independent organizations who run networks, to exchange lists of networks that are reachable via their network. So they would advertise their own networks to their peers, and they would advertise their customers to their peers. And that is replicated according to standards with the BGP protocol across the internet, and that's how it has grown organically since its inception. If we talk about each organization, they will have at least one label called an autonomous system number, or an AS number. For instance, I run AS 62129, formerly AS 198988, and it's just it's a label that says that people can identify the routes that I'm originating, as in advertising out, that are specifically on my network, and they can also identify what routes are transiting through my network. So at the boundary of each AS, routers will exchange network layer reachability information, or NLRI, using BGP. So at the boundary of each AS, basically lists of networks or prefixes in CIDR. So that's classless interdomain routing. So basically, it's not the old class ABCs of where the subnet masks are either 8, 16 or 24 bit. So they decided to use variable length subnet masks, which would allow you to, it actually allowed the IPv4 internet. It kind of gave people more time to move to IPv6, in which people like me just used the time to do nothing. Sorry guys, sorry everyone. But yeah, so in terms of what it does, you're you're basically saying, here's a list of networks like 8.8.8.0/24, and it's reachable via mine AS, like for instance Google's AS number 15,169. And you can see in this example where I actually I query the BGP router with the BGCTL command. You can actually see that I have 4 paths to Google's DNS servers, and 2 transits and 2 via my local awesome internet exchange INEX. Shout out to those great people who run that organization and the network, which has been a massive improvement and help to my company. And I couldn't help but recommend you, if you have a network or you're operating an enterprise network or a content delivery network or an ISP, certainly consider joining your local internet exchange. If you don't have them, maybe you maybe talk to the good folks at INEX or EuroIX who can help you. Big latency, so we're peering with Google, and from our data center, it's less than a millisecond latency to Google's DNS. So we're quite fortunate in Ireland with our connectivity, and I think a large part of that is due to the work of the people at INEX on our network. So just big shout out to them if they're watching. This protocol allows the internet to be somewhat decentralized and grow. We've already said that, and it works well most of the time because of well-intentioned, vibrant community of well-intentioned engineers. And then there's a number of activists and visionaries that try to lead us to a better place to address some of the flaws in it. And Job Schneiders, who works, with Claudia Yecker on OpenBGPD and on the project, people like that, watch what they're doing, watch what they're saying, and trying to understand what they're saying and implement it on your network. So BGP at an ISP edge, if we're talking about it, basically, for my router, so my AS to, let's say, my transit provider, so I'm AS 62129, and then one of my transit providers is Cogent AS 174. So what I need to do is, I want to get download traffic from my transit provider, so what I need to do is advertise the list of networks that are reachable via my network, via my router. So I do that with BGP. So I push advertisements to Cogent, and Cogent then hopefully accept them because they're valid, and program those routes into their routers and replicate that out to all their customers. And because of that, because I've advertised my routes out, I'll start getting traffic coming into my network. So the simple act of just advertising a handful of prefixes, which is about the amount I have on my own network, that allows me get all my download from my ISP. And then the upload traffic, that's a slightly different matter. So, but it's just the reverse. So, Cogent or AS174 will advertise the prefixes that are reachable via it, and I will accept them if they're valid and not, in any way wrong. And I'll program my routers with those routes. And if I do that, then I will upload traffic. I'll start to upload and route traffic out. So download is basically advertising routes to other people, and your upload is learning routes from other people. So you just bear that in mind. So on the local internet exchange, and a heavy influence on what I did on my own ISP was learning lessons from the likes of INEX and the people who run it. Let's talk about internet exchanges. So an internet exchange is, for the want of a better description, it's a switch with a load of routers connected to it, and each one of those routers would advertise BGP to everyone else. Now the problem is that you get an n-1 squared problem, in that if you have 101 routers on an exchange, you need to have about 10,000 sessions established and configured on all 100 routers in order for every member to exchange traffic. So each router needs to peer with everyone else. Root servers were designed to minimize this load, and it's quite nice. So if you see here, for instance, there's Hurricane Electric AS6939 and then Google. So Hurricane Electric, obviously, you can see has access to Google servers, or Google servers are reachable via Hurricane Electric. So they advertise that to the root server. But so are Google on the exchange, and they advertise those same prefixes to the root server. So we have all these other ISPs advertising their routes to a particular root server. So they have sessions established with the root server. And then the root server kind of aggregates all these routes and filters them, which is a very good security component of an internet exchange. And it's why OpenBGPD and BERD, those people want, the people who run internet exchanges wanted improved software for improving security to stop mistakes on member servers, member routers, causing internet leaks and stuff like that. So the root server actually aggregates all this, filters all the prefixes learned, and then re-advertises it to everyone else who's peered with it. And what's interesting about this is that by doing that, the traffic actually flows between the members through the switch, but not through the root server. So the root server is absolutely critical for the control of the data flow, but it's not actually forwarding the data in the data flow. That's left to the layer 2 switches in the internet exchange fabric, and it's left to the individual members. So effectively what the root server does is it says, hey Tom, your network wants to get to Google's DNS servers, go to Google's DNS IP, Google's router IP on the LAN there. And if it redirects people to that, or it directs routers where to send the traffic to, will probably be a better way of describing it. So that's kind of where we're getting onto. So that's why we started to use it in our own ISPs, that I wanted, well, maybe I can apply similar logic using switches in layer 3 in my own ISP. So BGP also comes in 2 flavors, and that's just something to be aware of. So you have eBGP, which is eBGP and iBGP on the wire look very similar. So between eBGP, you'd have 2 different AS numbers on the peering session. So one router from one AS, another router from another AS, and so that's an external BGP session, okay? And then you have to have an internal BGP session where you have 2 routers with the same AS number. So all the routers within my own organization will be running iBGP between each other, and then the routers between my organization and another one will be running eBGP. So if we look at standard routes, so I just we talked about it, forwarding a packet to a next hop that's usually directly reachable via a connected route. So for instance, let's say for this example, we've got a network 1.2.3.4 that's reachable via the blue router on the right hand side. So if we take if that's propagated out via OSPF or some other routing protocol, what we'd be familiar with is that 1.2.3.4 on the yellow router will be reachable via 5.6.7.8. And then on the first green router, it will be routable via 1.2.3.4 will be routable via 6.7.8.9, and so on and so forth. So you can see that you've a host directly reachable, and you can forward the traffic to it. Okay, so that's your standard routes. And then there's the concept of recursive routes. So the recursive routes are just we're building on it a bit. It's where the next hop is in BGP. The next hop doesn't really change. So the next hop will be, if it's learned from an external like, oh hey, I got this prefix from Cogent or AS174, I'll remember the Cogent gateway throughout my network as being that's where I need to send the packet to get to that destination. So the problem with that is that on the yellow router, it's not directly connected to the router that's advertised in 1.2.3.4. So the way we actually get around that is we supplement the IBGP route with an OSPF route. Okay, so so the blue routes are what we're learning through IBGP, and the green routes in the diagram are what we're learning through OSPF. So we actually use the IBGP route plus the OSPF route, or a static route it may be, or some other IGP route, and that allows us to get to the final destination. So it's just a little nuance that I have to say at first kind of wrecked my head, but you get used to it. You get Stockholm syndrome or something, and you kind of think it's okay. If we look at recursive routes, the supplementary route, so you learn via IBGP, but you need to also learn an additional route via static or OSPF or ISIS or RIP. I'm not endorsing ISIS or RIP or anything like that. I've never used them. So recursion is actually more common than you think. So this concept, and just to give you a kind of a simple example, so if we looked at a router here, we have a default gateway of 10.20.30.1. So if I want to route to somewhere that's not directly connected to my router or computer, I would use the default gateway. I need to send the traffic to the default gateway in order to get it to its final destination, or hope that it gets to its final destination. In order to do that, what we actually need to know, well, how do we construct a frame that would actually reach our default gateway? So we need an ARP entry, or a host route. So and OpenBSD, one of the things I like about it, is that you see the host routes or the ARP entries as host routes, and you see that 10.20.30.1 is reachable via E4, 8D, 8C, 1C, 16.6.4, and so you can actually see that. So just remember that your default route isn't enough. You actually need the ARP entry for your default route to get out to its final destination, hopefully get to its final destination. The reason why I use hopefully is that it's not guaranteed. You need a lot of other things to work for that to happen. So if we look at the recursing through routes, just an example from our network, and I've kind of modified the IPs for simplicity of reading. But you can see here that we have 8.8.8.0/24. So I'm asking BGP-CTL to give me what routes has it learned via BGP, and this would be like our routing information base, or like a list of routes that are available. And we see that we have 4 routes for 8.8.8.0/24. And we can see that some of them are learned directly from Google because they're on the same internet exchange as we are. And we also learned them via 2 transit providers. So you see 174, AS17. So you see the AS path. And the AS path is a nice, interesting thing in BGP that allows us to select routes, hopefully based on the shortest path between the shortest AS path. So to reduce the number of networks we're transiting through. And you can see that while 1.2.3.4 and 4.5.6.7, so the routes in blue, black, red and yellow, they may not necessarily be directly reachable via my router. So it's an important thing to understand. So in that situation, what we want to do is we need to learn supplementary routes. So if we actually look at the other routes, we know that 1.2.3.0/24 is reachable via 2 gateways. And you'll actually see that 4.5.6.0/23 is reachable via 2 gateways. And we also see that 8.9.10.9 is reachable, or 8/29 is reachable via 2 gateways. And then the routes in blue there, the 11.12.13.0/28, they're reachable by the same gateways. So what you're seeing here is obviously I have 2 links from this router that I ran that command on, and I have two gateways, 10.10.10.2 and 10.11.11.3, and that pretty much replicates what we have in production. We have two routers, two gateways with two layer 2 networks to two separate layer 3 gateways in case there's an OSPF problem or there's an issue with a switch or something like that. So we try to do that on both LANs. So the routing information base versus the forwarding information base. So what I'm trying to show here is that when you actually query the routing information base, or the forwarding information base, so root minus T0 minus N show, that's actually querying what's programmed into the kernel. And we see that 8.8.8.0/24 is reachable. I'm not too fond of the way it displays in the output of the routes, but you can see that it's 10.10.10.2 is the gateway. So it's already resolved. If I go back one slide, it's already resolved that it's reachable via. You can see the selected route, the valid one, which is the first route on the list, and you can see all the flags. So if you want to see the flags, it's helpful. BGP-CTL will actually show you the flags of which route was selected. And you can actually also see that the kernel has actually selected that route for you and presented and shown it to you, the forwarding information base. So that the forwarding information base is just the routes that are selected and programmed into your kernel or your routing hardware, if you have such. So switch strengths. What are the strengths of switches? Well, they can forward in hardware at line rate. Terms and conditions apply. Some packets are sent to the CPU for inspection. It can also filter packets in hardware at line rate, but it's generally IP header filtering. So you can't do stateful inspection and stuff like that in hardware on the switches that you typically you'd try this on. Our network, so for the forwarding capacity, the huge forwarding capacity, and in our network we use 4 Arista 7050QX32s, 9610 gigs and one rack mount unit, which is amazing, and I think I already went through the 2.5 terabits and 1.4 billion packets per second, so that's the reason why we did. But there are limitations to switches. ASICs and switches have finite memory capacity for forwarding packets and frames and remembering which destinations to send to what port or what next hop, and that's important. And this memory is TCAM, and it's so important, and it's one of the things that when you're looking at a switch, not all switches were created equal. You will have an upper limit on what max MAC addresses it can learn if it's a layer 2 switch, or host routes if it's a layer 3 switch, and indeed what maximum number of access control lists can it handle. The access control list will be allowing you to do your filtering, and not all switches were optimized. Not all switch profiles were created equal. Forgot the equal there, but it's optimized for either layer 2 or optimized for layer 3, and that's why we ended up going with 4. So we had a pair of switches that were optimized for layer 2 operations, and then we had another pair of switches that were optimized for layer 3 operations. Know your hardware usage. Make sure that your switch vendor, whoever you choose, has the ability to show you how much TCAM space you're using. And in this case, like you can see here, we're consuming about 102,000 routes in our setup. So this is just taken yesterday from one of our routers, out of a possible 393,000 routes. So that's a pretty nice switch, and they do have quite a big capacity. And the way they do that is they use ALPM, which is algorithmic longest prefix match. So Arista allows you to tune the TCAM profile for routing, and that in that case, when we use ALPM, we can get more routes programmed into the TCAM. The ALPM upper limit is shared between your IPv6 and your IPv4 routes, So when you're moving to IPv6, which you should be doing, you just need to be mindful, like what I would do is start off easy and just see how many routes you add in with IPv6 and how much actual TCAM space is it chewing up. So if we analyze the route table, which is why I wanted to analyze the IPv4 internet routing table, was I wanted to see how many routes can I program into these switches. We know they're limited, so how do we do it? So I did a god-awful script that pretty much just did a grep -c on my route table as programmed or learned by my routers, and just to get an idea of what sort of prefix count we had. So with the routers that we have one default route. We have 10/8s, 11/9s, and these are all obviously very large networks, /8. The smaller the prefix number, the much larger the network it would be. And then what you actually start to see is that a dramatic increase from /21s through to /22s and 23s and 24s. You actually see the bulk of networks being in, let's say, /24s and /22s. So we see quite a lot of prefixes. If you were to add all of those up, that's 815,000 routes. It's won't fit in all our switch, so we need to do something. Now, one of the nice things to remember is that this is all just for my upload traffic. So my download traffic is taken care of by advertising. So as an eyeball ISP or an ISP where users are consuming data, connecting to other websites, connecting to other people on the internet, this is not a huge issue for us. We're getting lots of download, and we just now need to deal with the upload, and that's what programming our TCAMs is about, is getting an optimal flow for our upload traffic. So if we look at our TCAMs can hold 393,000 routes roughly, but it'll be shared across 4 classes of routes. So you have your IPv4 unicast routes, your IPv6 unicast, and then obviously you have your IPv4 multicast and IPv6 multicast routes as well to worry about. Our hardware switches also will need to peer directly with networks on our local internet exchange. So not all other ISPs will want to establish the type of sessions where they would actually connect directly to my OpenBGPD routers. And in that case, I would actually need to use my Aristas to learn to learn other people's prefixes directly on the Arista switch on the exchange through the root servers and through direct bilateral peering relationships. You can finding out how many prefixes are needed to an exchange you're joining. Look at your peering DB, look at the peering DB entries for that exchange, look at their looking glasses. These looking glasses basically give you a view of how many advertisements or how many routes are being learned and advertised and distributed by your root servers on your prospective internet exchange. So in this one we can see from live data just from yesterday from one of my routers that there's about 65,000 routes on INX LAN 1. So it's about 66,000 routes in total, okay? And you can see that I have 2 sessions because they have 2 root servers for redundancy, which is pretty awesome. And then obviously if we look at INX LAN 2, there's we're learning about 2,500 routes on that one. So you can see it in red highlighted, the prefixes received, and we're accepting all the prefixes we received because INX have filtered them for us, which is great. And so summary of requirements now that we've done a bit more analysis. So we have 66,000 routes on INX LAN 1, we've got 2,500 on INX LAN 2, so we've about 70,000 routes that we need to program directly onto our switch. And that's going to vary from time to time, so you just need to track that as new users join your internet exchange or new ISPs join your internet exchange. And we also want to have space for IPv6 addresses, which we should be using already. And thankfully that's a smaller number. It's 89,000 routes for the entire routing table as opposed to 800,000 routes with the IPv4 internet. It is also worth noting that the IPv6 will chew up more TCAM than an IPv4 address. They're bigger networks. So just to be aware of that, so start small when you're doing it, and then progressively increase your routes that you're allowing into your hardware switches, so that you're not overrunning your TCAM tables. If you look at it in terms of we need 70,000 for the internet exchange, about 90,000 for IPv6, and it'll likely we have a 393,000 route capacity. So what we're going to do is we're going to say let's allow 50,000 routes from transit plus default into our router. So that's what we wanted to learn. And so how we did that, so we did the analysis, and what we can see is that there's about 39,000 routes shorter than the /18. So so from /8 to /18 plus default is about 40,000 routes in total. So in that kind of gave us our benchmark. So if we compare why would we want to use full tables versus default route, it's something I haven't discussed. And the full tables will be, it allows for granular view of what networks are available from a given transit provider. So they're very helpful in diagnosing issues. They're also very helpful in diagnosing the path, like what path does a particular packet would take when you send it to a particular ISP. So not all transit providers were created equal. Some will have shorter AS paths than others. The disadvantage of it is that obviously it has higher memory requirements, higher hardware requirements, higher processing, and it's longer to convert. So when you start a BGP session with a default route, it'll come up pretty much immediately. While a routing, when you're trying to pull in 800,000 routes, filter them, install them in your route table, that takes a bit more time. Typically under a minute in our network, in around that. So you can see, a couple of seconds versus a minute. It's a fairly big change. It's at least an order of magnitude. If we look at, let's say, the default route, the problem is that you have a very coarse failover of traffic. So it's either on or it's off. That's your failover event. Even if so, that's why having two tables, being able to granularly fail over. So you may prefer one ISP, but maybe a network like Yahoo is not available from your preferred ISP. You can just direct the traffic that's not available via your preferred ISP via your second ISP, which might be a slightly more expensive for transit costs. So there's no visibility with default routes, but it's faster convergence time. So what I wanted to do was to reduce the risk. So to reduce the risk of black hole and traffic. So what we said was let's accept large networks. So if someone's advertising a /8, chances are they're fairly big. And it's an assumption. It's not always translates into reality, but you have a lot more IPs in it. The probability is that they will use more traffic. So at least we're actually comparing all the very big networks down to /18s, and then what we do is we summarize the 19 to /24s as a default route. So but we also use the routes, all the routes from the internet exchange. They're programmed directly into the switch hardware. So at least we have all the local traffic is being granularly routed and failed over, and preferring in naturally the actual the internet exchange. If we want to learn routes that from our internet exchange, and we want to accept pushing it into other hardware routers in our network, on our external routers facing those particular exchanges, we need to paint the routes so that we know this is learned from a local exchange, please accept it and push it into the TCAM, even though it's a very specific small route. And so what we do is we use BGP set community commands for that. So in our Arista routers, we used the AS number for the INEX AS number, which is 43,760, and we just basically tagged any routes learned from their root server on LAN 1 as 43,760:1, and we set the community for any routes learned on INEX LAN 2 as 43,760:2. So that was just, and then our OpenBGPD routers, what we did was we said, right, how do we limit our transit? How do we limit what networks we're learning from transit so that we don't overrun our TCAMs? And it's very simple. We just say by default we drop all the prefixes going into the restricted fib routers, the hardware routers in our organization. And then with, as you can see highlighted in red, we basically say we'll allow any prefix from 8 to 18. So that covers that range of prefixes we want to allow that we know won't overrun our TCAMs. And we also allow the default route. And interestingly enough, at the very bottom, we want to allow specific routes that we learned from the Internet Exchange to other hardware routers with restricted TCAMs. And the way we do that is using that anything that was painted with the community that we mentioned earlier, the 43,760:1 and :2, that those will be accepted and pushed into the TCAMs as well. So this is an OpenBGPD filter config for that purpose. So then protecting our hardware routers TCAM from overfilling. So the way we do that is we basically say, hey, let's set a max prefix out. So thanks Claudia for implementing that feature. I think I asked for it years ago, and it was difficult that's a difficult feature to implement, because if you can imagine, you have to monitor and manage all the prefixes and count the tables, the prefixes you're advertising out and withdrawing, and you have to track that somehow. So I have to say that was pretty impressive what that feature. So it looks very simple there, but I'm sure it wasn't so straightforward to implement. So thank you for that, and sorry for not testing it more for you. The other item I just wanted to say, so there's a max prefix limit out. So that's what our OpenBGPD configuration is on the top. And then on the bottom, we will see, it's not there. Nice. So we'd have a max prefix limit on the, so love that. So the Arista, on the Arista config, there's actually a missing one there. It should have max accepted prefixes, max prefix received. And Arista's newer versions of Arista, recent versions of Arista's also have a max prefix accepted. So you can actually do some filtering as well. So even if your upstream router is sending you a load of traffic, you can filter some out so you don't close the session based on them sending you loads, but you can close the session based on them sending you too much that you would accept. So there's two different settings, and just it's important to know the difference. In terms of setting this up, you need to work with your transit providers. To work with your transit providers to do this, you need to get them to set up a multi-hop session. Ask them to advertise the full route table plus the default route. Agree 2 loopback interfaces with them for each of your routers, and agree a static route to the first loopback and via the first hardware router for the first BGP session, and agree an alternate static route for your second loopback via the alternate hardware router. That's an important point. There's no point in having redundant routers and then having the same next hop. So you're creating a single point of failure. Another thing is be careful with next hop validation, because your loopback, sometimes they forget to add static routes, and and so it's something you don't necessarily have to do with directly connected BGP sessions. So often it all looks fine, but it's not being selected, and the reason it's not being selected is failing next hop validation, and that happens on at least a third of our ISPs that provide us bandwidth. Again, the normal distribution was, the pool that we were surveying was 3 we had, and one of them just didn't get that concept, and you're trying to explain to someone in support what's going on. So just watch that one. That's the main thing. And if you explain it to them like that, hopefully someone senior enough will be listening to you on that. In terms of the static routes for the multi-hop sessions, here's an example where we're pairing with Hurricane Electric. So on the BGP route reflector 1, we route via route reflector 1, so you can see the purple kind of path that we will take. So give them routes that would allow them to have the inbound path via your first hardware router to your first route reflector, and then have the alternate, the diverse one, will have basically your Hurricane Electric routing to your second route reflector via your second hardware router IP. So the max prefix tips, if you're more than one session between routers, I would say raise the limit slightly in one session. So the internet grows organically, and it's not really cool to be protecting yourself from overrunning your TCAM tables or misconfigured BGP sessions. So what I would say is that if you have maybe 1,000, a couple of hundred routes on a small peer, or 10 or 20 routes on a small peer, and then maybe added 50 or 100 to the second one, you're going to limit the damage quite considerably with that if it's a misconfiguration, and it'll trip alerts all over the place. At least the first one will warn you that there's some problem. The first session going down will warn you there's some problem, and it'll also give you time to remediate it without pulling down your entire routing infrastructure. The other point is that so if it's just organic growth, you want, why are my sessions down on my router ones? Okay, it's because the internet table just grew by 10 and it just tripped the limit. And then you're still routing on router 2s, your second branches of routers, because they have a slightly higher limit. And then if it's a catastrophic failure, like someone's sending you full tables and they should only be sending you 10 routes, their session's going to blow through those limits anyway, so you're still getting good protection there. Advanced recurrent sessions, all the traffic is handled by the hardware routers. We're utilising our local exchange. We use SFlow on the switches, or we can use SFlow on the switches to sample and detect DDoS traffic, and we're not worrying about packet rates coming through our CPUs on our software routers. And it's low cost compared to a full spec hardware router implementation. We can also have better resilience to high packet rate DDoS because the routers can handle higher throughput. So that's kind of nice. Disadvantages: risk of black hole in traffic to our default transit provider. This is mitigated by the fact that we obviously learn the bigger networks, and we also, our internet exchange traffic is not in any way restricted. The ability to learn small routes are not restricted on our local internet exchange. So it's only an issue from the prefixes from 19 to /24. Still an issue. It's a more involved setup. That's another disadvantage. It's less flexible filtering, so no software routers in the data path. That's the other issues I've come across is URPF can be a challenge with hardware switches. They can have slightly different kinks, like not accepting, not allowing the default, not using the default route as a valid next hop. That's an issue, and you don't want to be blocking traffic like that. And it's not, this particular setup is not useful for content delivery networks. What I mean by that is, so if you're a content delivery network, your outbound traffic is key. Your outbound traffic is you don't know which /24 on the internet is going to pull as much of your traffic. One of the /24s out of the 815,000 routes in the internet. And in fact, Paolo Lecende did a brilliant talk at an INEX meeting a few years back, and he was talking about working in a content provider, and they did something similar like this, but they had a problem is that they're a content provider. Paolo Lecende is the author of PMACCT, and he's a great guy. I met him, I had the pleasure of meeting him, and he's very affable, very encouraging, and just really nice. So big shout out to Paolo Lecende, and he is actually, that talk was an inspiration, that talk, and we actually modelled our ISP and changed our whole infrastructure based on the ideas that he discussed at that INEX meeting. And it's one of the other benefits of being at INEX, being a member of our local internet exchange, is that you actually see and meet people like Job Schneiders, like Paolo Lecende, and you learn from them. So in terms of running, what he did, or what he was suggesting to do, is run NetFlow and SFlow on the switches, and work out which routes are actually using all that need, which destination IPs are pulling the most amount of traffic. And then you check and you compare it, is the path that they're taking via the default most likely, is that optimal? If it's not optimal, program in an exception route into the hardware to allow it to maybe optimally route via a different transit provider or a different internet exchange. So that is, you program the top destination prefixes where the default route is not the optimal path, i.e. IP exchanges or better IP transit, internet exchange. Sorry. So other ideas to improve reliability. Well, I was discussing these types of things with at BsdCAN with the likes of Claudia Yecker and Peter Hessler. Hello lads, and thank you so much for taking the time to talk to me. And I think that's one of the reasons why I love coming to BsdCAN, is you get to hang out with some pretty impressive people, and they're very knowledgeable, and two, they're very friendly. They're willing to listen and willing to help you in any way they can. So I can't thank the community enough. One would still want inbound traffic through the hardware routers rather than black hole the traffic like what my setup would do for the /19 to 24s, is route them to a software router. Again, you're only dealing with upload traffic, so you still have the hardware advantage. You'd only want to do it for upload, so you have the advantage of the hardware routers. So food for thought and a request for feedback. It's not an RFC, so just to be clear, and just more, it's discussions. I was just wondering what people thought of maybe using default plus exception routings. So you pull two feeds from transit providers, and you select one of your transit providers, for instance, and then you would diff the prefixes available from transit 1 and transit 2, and then from that you would see that the routes. So if you say do default via transit A, then what are the routes that are only available via transit B? And the routes that are only available in transit B, then you would program them into your switches. And then you would monitor the differences obviously continuously between those two routes, those two transit providers. And then in the event of a failure of one of the transit providers, or a massive outage like a C-fiber cable cut, that you would actually be able to flip the default and then do the exceptions of the other direction. And I was just wondering what would be involved in this and what do people think. So please email me or Twitter me or even have a chat. I don't mind a robust discussion on it. I think it's a good idea, but then again, I'm not taking into account everything, and maybe people who are operating bigger networks than mine might have an opinion that might be that some aspects of it. What else is there? I'd just like to say thank you. These are paintings that my daughter Sophie Philomena Smith made for me because I'm a bit of a BSD fan. And I'd like you to donate to your preferred BSD foundation and the BsdCAN, and support the Ottawa not the Ottawa mission for helping people who are less fortunate than us. Again, thank you so much to Dan Langell and the team at BsdCAN. Your work and effort has made my life better and made it more improvement, so I can't thank you enough. So again, just thanks everyone, stay safe. And remember, flatten the curve.